Today we're going to be talking about Escher, but his work was really very mathematical, very precisely planned. Now, this is an intriguing slide because I can see Caroline in this slide. Caroline, you should perhaps tell us about this exhibition.
This was an absolute pleasure. I was in Madrid in Spain, as you do. I was brought up there, so it's not surprising. And I have a wonderful colleague who teaches maths at a polytechnic, but he, outside of normal work, he does a lot of maths engagement. He's a mathematician. And he's like, there's an Escher exhibition in town. So we raced over there and we had a wonderful time. And the thing is that Escher isn't just, we will see some of the things he's famous for here, but it's all about perspective. He must have had an extraordinary brain to be able to actually reproduce ideas that, like the impossible staircase. Have you heard of the impossible staircase? He managed to make a picture of the impossible staircase, and
so many different images and so much maths in them.
And you can see that the walls curving, and he can actually make it look real. And it is, yes.
And what you see here is quite a lot of other people looking out a window, a little man sitting on a bench, somebody walking along a corridor in an art gallery. But then magically, the people who created this exhibition were very clever, because they created the possibility of you seeing your friend in Escher's picture. I think that's just extraordinary. So what about Escher? Well, he was born right at the end of the 19th century and lived until 1972. So he was a graphic artist, and he did a lot of woodcuts, lithographs, and mezzotints. He explored space in different dimensions, and in particular, filling of space by regularly repeating patterns. That's called tessellation in mathematics. He worked with mathematical objects and also mathematical operations, including hyperbolic geometry, impossible objects, as Caroline just mentioned, explorations of infinity, reflection and symmetry, as you saw, in particular reflection in the earlier slide. With perspective, well, of course, all artists work with perspective, but he's intrigued by perspective and does a lot of strange things with perspective.
He goes into rabbit holes with perspective, doesn't he?
Right.
He really investigates it deeply and very successfully.
And he does things like having creatures crawling out of 2 dimensions, very definitely in 2 dimensions, and then suddenly coming out of 2 dimensions into 3 dimensions and then back into 2 dimensions. But of course, you're seeing this in a 2-dimensional picture, but the 3 dimensions looks incredibly real. But he's doing this in order to explore the differences and the sort of merging of the different dimensions and what we see in them.
And that's without computers, no CGI, just
exactly
pen and paper.
And then polyhedra, and we'll look at some of those. Now, he didn't have any formal mathematical training. Apparently, he didn't do terribly well in school, as a lot of other geniuses. That applies to a lot of other really high-performing people. He believed he'd no mathematical ability, but he did his own research into tessellation, which we mentioned earlier, and he interacted with mathematicians, with George Polyer, Penrose, who was at Oxford, Coxeter, who was an Englishman who spent most of his career in Toronto, Canada, and then the crystallographer, Friedrich Haag. Now, of course, the way things fit together in space is very, very important in crystallography, how matter is fitted together. And a very common example of that, of course, is the beehive, the hexagonal tessellation there. So that's Escher. So let's explore some of his work. Now, this picture is one of my very favorites, and we've got it hanging in our lounge at home. It's called Night and Day. And Escher put recognizable images of living things into tessellations. And he liked to use the theme of metamorphosis, or changing of one form to another. And birds transform into fish and fish to frogs, for example. Now here you see the light, the white day, gradually changing into the dark, the black night, and the birds flying across the screen there, across the picture rather, and the white ones flying from left to right, and the black ones flying from right to left. And
there's symmetry. If you look carefully at that picture, the two rivers are symmetrical. The towns, there's two similar. They're not identical, but they're very similar pictures. You can see the symmetry, and this. I could just stare at this picture for hours.
There's so much you can.
The detail.
There's so much you can see in it, isn't there?
And just thinking about the mind that created this, who thought he wasn't good at maths. Oh,
hello. You're Caroline, back in the museum, the same exhibition. And you can see here, it's not exactly as we saw it in the day and night, because we've got mirrors now, like the Hall of Mirrors at Versailles, parallel mirrors that are creating many, many images and images of images to give these birds in 3D space. And you've got them, if you look, they are reversed. So the white birds are, if you look, go back along a line, flying towards you, and then the next one's flying away from you, and the next one behind that is flying towards you again. It's hard to see with Caroline as well.
Yeah, you can see that. Yeah, it's hard to see with the line of birds at the top there, but you can see it with me. And then if you look down to the right, you can see a bird flying towards you, and above that, so if you look at the reflection that's that way, that way, behind me, that way. There's the one lower down that's flying towards me, and the one next one up is flying away from me.
Yes, and it's definitely not Escher, but this is created as part of this Escher exhibition at Madrid, and it's the same sort of theme of birds repeated. And here you see it again, the same display, repeated again by reflections. I think that's amazing.
It was. If you ever get a chance to see the Escher exhibition, please go. It travels around the world. Go.
Well, you can also go to Holland and the permanent museum there with a lot of exhibits, not as sort of fanciful as this, but much more detail about his work and showing you his various woodcuts and stages at which, you know, of the woodcut, the way he made his woodcuts. Now here, this isn't Escher. This is a compilation inspired by Escher, with Caroline at the back there. And this, the front there, that fishes, we'll see that again. That's a bit of Escher. But he didn't do works like this with sort of different, you know, big changes from one to another in this way. At least I could be wrong, but maybe I'm wrong. But it seems to me it's more something like the mirrors one, inspired by Escher. Now here we get onto some of the real Escher.
And this is what inspired Escher, as opposed to inspired by Escher. It was the other way around, what we're seeing here.
Yes, well, as a young man, Escher went and worked in Italy for a few years, and he took a trip to Spain. I rather imagine him as a young, a bit romantic really, as a young backpacker, like young people do in their gap years now. But he would have had all his artists' stuff with him, so he could do his painting and his work.
And maybe he travelled in style and had his own carriage and
Yeah, I don't think so.
Oh.
No, I don't think he was a rich aristocrat from Northern Europe. No, he was inspired at Alhambra, which is a Moorish palace in Granada in Spain. The Muslims didn't believe in depicting the human form in any way in art, and even living creatures. So theirs was entirely abstract art. And you see on the left a designers Alhambra, which is based on threefold symmetry, based on triangles, but you can see how those shapes are all fitted together. And in the middle there's just a sketch from Escher's notebook, which was a study of the design on the left. And then a few years later, he made that into not just a design, but an actual art production, which he called Hexagonal Tessellation. And the subtitle is The Study of Regular Division of the Plane with Reptiles. Now you can see if you take where, for example, the 3 points of rotational symmetry, where you get 3 of the legs
the 3
meeting.
Intertwined.
They meet at a point, and then the green rotates into the red, that rotates into the lighter cream colored one. So you can rotating about the diagram about a point. Now that's threefold rotational symmetry. So it is essentially a development of the symmetries. We talk about symmetry not just in mathematics, not just to be reflection, but to the symmetries, plural, are all the different sorts of ways in which the diagram transforms images of one motif or small part of the diagram. You can imagine them moving around or by reflection to another copy of the same motif. So there we have.
Actually, I'm glad you pointed that out, Tony, because I hadn't actually noticed that. I've seen that in other images, but I hadn't noticed that that's the one place. Oh, you got it with the heads as well. I was going to say that where have you got that? Because with the front legs, you don't have that repeated pattern so much.
Well, their cheeks meet.
That's cheeks. What I'm saying. It's the heads, the cheeks. You got that with the 3 heads, and then you got that with the rear one of the rear legs, and I hadn't noticed that. So that really does help you see the rotational symmetry there. But it's just mind-boggling that it really just does continue, and you
can look at these things, can't you, on and just get absorbed in them.
And keep noticing different things.
So at a recent Happy Maths Hour, we talked about spirals and introduced the idea of stereographic projection.
Now I'm just going to give you permission here to just sit back and watch the show. So feel free to jump in, but feel free to just watch the show and just accept what's being said, because this is one of the areas where I struggle. That doesn't mean you will struggle, but it's okay to just let it flow over you and just enjoy the concept. Sorry, Tony, go ahead.
Well, this is used in map making. So one of the projections that puts the globe, what we have on the Earth, our continents and cities and all the rest, onto a flat map in the atlas is stereographic projection. It's not now the usual one used, but it is very much the way that mathematicians study spherical geometry. Now that is geometry on the surface of the sphere. And you see in Escher's work there called sphere spirals, you can see a square grid on that, little squares. They look a bit distorted perhaps because they're on the surface of the sphere, not onto the flat plane. Now what you see in yellow on that is a spiral on the surface of the sphere, but what it maps, it's a mapping considered as a mapping from the sphere to the plane or from the plane to the sphere. What it is a mapping of a spiral in the plane, okay, which is the same width everywhere. Now,
So if it was not on a sphere, would it just be like a cylindrical spiral?
yes.
Okay, so it's the
So
equivalent. Equivalent. I mean, I don't even know what language to use here. Is it the equivalent, like a spherical equivalent of a spiral in? If it's just a cylinder, is that that's not Euclidean, is it?
well, no, it is actually, because if you imagine taking the
you
label,
can flatten a spiral. You can flatten a cylinder, so it is Euclidean.
Yes.
Okay.
Yes. So, but this is not between a cylinder. This projection is not here. It's not between a cylinder and the plane. It's between a sphere and the plane. And you see the diagram in the middle, lower down, is showing you that the lines go from the North Pole, and they project the points on the sphere to, I mean, when I say project, I mean, it's the point P on the sphere has an image P dashed on the plane, okay? And all the points of the sphere have got images in the plane. And the center of the sphere, O, its image is the South Pole. And imagine a map imagine the Earth with the UK where we are, or South Africa where some people listening to this are, or wherever you are on the Earth, then your town would be mapped onto the flat map by a stereographic projection like this. And it's another thought is, where does the North Pole map to? It's different from every other point.
And it's this is where the thinking, if I'm correct in what I'm thinking here, this is where a mathematician has no limits. There's a clue for you. An engineer, which is what I am, you're like, well, that's just pointless. It's not possible. So there's no point. Let's make it as accurate as we possibly can within specifications, within certain tolerance. And within that, we're done. Not a mathematician.
We can travel to infinity in our minds. Well, everybody can. I mean, I'm not a real mathematician. I'm just a teacher. But no, with mathematics, everyone can fly to infinity like space fiction. But it's not. It's something else.
Can we just go back to that for 1 second, Tony? Because I found it is fascinating that from that North Point, you literally cover an infinite 2D plane, as in a 2D plane that never ends, because the angle that from the North Pole is actually parallel. Well, it's not. I don't know if it's parallel. Well, I suppose it is parallel, isn't it? So that's not a 2D plane. That's messing with my head again. But it just keeps, the angle keeps getting closer and closer to 90 degrees, so that it's extending just to infinity, literally. And so to project one sphere, you can project it across an infinite 2D plane, which I just think that's, I really like that. I'm quite
Caroline,
happy to sit and absorb that.
How about this, Caroline? You have an infinite flat piece of paper.
Yes.
And then you wrap it up and it covers the sphere. But in so doing, there are no crinkles in the paper.
Isn't
that
that's
lovely?
Messing with my head again. But yes, it's lovely. Yes, it's again a mathematical concept which is real, as in it's mathematically true. It's and the thing is, it's true. It's infinite, and then you can actually put it on a sphere that's only this big. How? Because there are infinite amount of points on a sphere. It's yeah.
And there are infinite number of points in the plane. And there's a one-to-one correspondence between the two. Okay, let's move on to the stellated dodecahedron, no less.
Yeah.
So it's called a dodecahedron because do means 2 and deca means 10, so that adds up to 12. Hedron means, well, in Greek it means
faces.
faces. So this is 12 faces, and that's f equals 12 on my slide there. And there are 30 edges and 12 vertices.
In a dodecahedron that's not stellated, it is just like a ball with 12 faces. They're all pentagons and doesn't have the little peaks sticking out.
The sculpture there at the University of Twente in Holland, I think, is one of, I don't think Escher actually produced it himself. I think it was produced from his designs and cast in some metal there. Beautiful thing. But what you see in gravitation on the right is turtles, yellow turtles and blue turtles and green and orange turtles. And each of those little sort of pyramids on the stellated dodecahedron replaces the turtle shell. And you see the turtles have got no shells, not proper, not their original shells. Oh, I thought they were somehow humanoid, and then I thought they were monsters, and then they're actually creepy, aren't they?
Yeah, I don't like them.
But it
I
is
use teddy bears, but they are clever, definitely clever.
Yes, and they're poking their heads out of the little trapezoidal doorways.
Yeah, I wouldn't want that on my wall. It'd give me nightmares, but it's fascinating.
And then I put in here a picture of the pentagram. So that shows you what Caroline was describing. The lines there, if you start at one of the outer points and carry on, imagine drawing that line, you have got 5 edges. Before you get back to your starting point, you've got 5 edges. And then inside that, you've got a pentagon, and you can put one of these pentagrams, which are the stars, inside it. And inside that, you can put another one. And inside that, you can put another one. And so it goes on.
Guess what? The engineer has to stop at some point, no matter how fine he can make he or she, not he, I'm an engineer. What am I talking about? The engineer can make the drawing. But the mathematician never needs to stop. It can go on to infinitesimally small. That's, yeah, I just love that. Just let your mind
infinitely large, Caroline, because that construction can carry on outwards as well as inwards. Wow.
Infinitely. Love it.
Okay, so you can see what pleasure, obviously, Escher had himself in creating these mathematical images, and also gets given to other people. Now we'll move to something else. And that is, people think of geometry as the geometry they learnt at school, which is Euclidean geometry, the classical Euclidean geometry. And that's on a flat plane. And there you see it depicted by the middle of those 3 images, angels and devils. Can you see the black devils? First thing I see is the angels. I live with the angels.
Yeah.
But actually, funnily enough,
could be bats. We could just call them bats. They don't have to be devils. But in the depiction, you can see the arms. They could be bats. We could call them bats. I don't like devils.
No, I think they're devils, definitely. Yeah. In the circle limit thing, it's the devils I see first.
Yeah.
The one on the right.
The one on the right. Yeah, the circle limit is it's the circular depiction of that. When you say circle limit, it's not. It's is that the hyperbolic?
That is. Yes. Okay. That is. But I mean, actually, the mind plays tricks, because one minute you focus on the angels, and the next minute on the devils.
Yeah, it's a nice optical illusion. It's just the fact that this is where Escher went. It wasn't enough to make these incredible 2D images. He had to then depict them on a sphere, and then again in a representation of a mathematics it's called hyperbolic. You'll see it in a minute. But if you notice, the the angels and the devils get on the circle on the right, the angels and the devils get smaller and smaller and smaller as they go out. But mathematically, they're not smaller.
No, isn't it? That is amazing. So we've got 3 geometries here, all depicting the same tessellation, but the one on the left is on a sphere. On the surface of the sphere, you've got the angels and devils fitting together in this repeating pattern, and that is spherical geometry, or elliptic geometry, as it's sometimes called. Then the middle one is, as I said,
just for those of us that aren't experts at this, does that apply to cones as well, the elliptical geometry?
No.
Okay,
no.
Just checking.
It's the geometry, as far as I understand it, it's the geometry on the surface of a sphere. Well,
okay.
Not really, even that. Okay, it's a particular sort of geometry with some axioms, which we will explore in a minute. Okay. And one of the models for it is the surface of a sphere.
Okay, we'll just leave it at that for now. Thank you.
Yeah, that's as I understand
it.
Just
because when you said elliptical, I'm imagining when you do a cross section of a cone where you get an elliptical shape. So.
That's a good question. That's a good yes, because you get the various conic sections, and the ellipsis and the hyperbola are both conic sections. Okay. So when you come into the mathematics, there's something called elliptic functions and hyperbolic functions, and well, anyway. Basically, the maths is translated from one to the other, and the correspondences are there.
The conclusion I come to here is that this man who thought he couldn't do mathematics was like, oh, what? He's interpreting all these concepts that I'm like, okay.
Caroline, I don't think he listed the axioms, and I actually don't think he worked with the formulae. Not much,
no, but
anyway.
He used the concepts to create his art. I'm not saying that, he doesn't have to put them on paper. He's represented them physically. I just think it's amazing. Right, okay, sorry. Keep going.
And the book that I took these from is a book that I've had for many years called The Magic of M.C. Escher, published by Thames and Hudson. It is a beautiful book. And so, and you can see with the pages, I found those diagrams in order to compile that. Yes, so now, what is this? Just as spherical geometry is on the surface of a sphere, one of the models, apart from the circle, another surface on which we can think of doing hyperbolic geometry is on saddle-shaped surfaces. Now you can see these cooling tires from the power station, Didcot power station, I think it is. You can see the cooling towers. They're not cylinders. They are they curve inwards as you go up. There's an inward and then an outward curve, and as you go, if you're on any one point, as you go around them, you sort of dip down. Or if dipping down is, as you imagine, that's a saddle between 2 hills there in the picture on the left. And that's another surface where which can be a model for, or can be the surface on which you can think of hyperbolic geometry playing out.
Is it the same on my scissor handles?
Yes, and on our bodies we've got a lot of these these parts of our bodies, like the surface where between our thumb and our first finger, we can go up the thumb and up the first finger, or we can go down onto the back and have our hand on the front of our hand. So right in that dip, we've got a saddle. So everybody's, lots of saddles everywhere, really, once you start looking for them. And, of course, on a horse. I mean, not on a horse, but what you ride, what you put on the back of a horse. Okay. So now here's a very geometrical picture.
But the horse does have that, because they do have that. It goes up and down, and it goes along either side of the horse. It goes up to the neck, and then it goes up to the rump. Goes up to the neck, up to the rump, and then down on either side. So the horse does have that shape as well.
Yeah. So that's the saddle shape, saddle surface. Okay. Now here you have a mathematical sort of representation of the three different geometries. You have what is called positive curvature for elliptic geometry, or spherical geometry as it's often called. You have Euclidean geometry, which has no curvature, everything's flat. And you have hyperbolic geometry, which with negative curvature. Now, what we're talking about here is the shortest distance between any 2 points, which is a straight line, or the technical term for it is geodesic. Okay, that's the shortest distance between 2 points. And it is what everybody thinks of as a straight line in the Euclidean plane, which are the top of those pictures. Now, on the left with with elliptic geometry, you've got positive curvature. So on the surface of the sphere, the straight line, or geodesic, is a great circle, like a line of longitude, a part of a line of longitude. Okay.
This is a concept that I still haven't managed to visualize it. I've kind of seen it, and I've done it on a ball. So if you actually draw a line on a ball, it is a curve, and if you look at it from up above, it looks like a straight line, but of course it isn't. It's on a curve. If you look at it from the side, it is on an arc, but there is no shorter way of joining those 2 points apart from drilling through the earth. which if you have a balloon, that's going to destroy the balloon. So that's not an option. That's a nice way.
But you can drill through you can drill underground. But then
it might get a bit hot.
But you wouldn't be on the surface, and the whole point of this geometry is it stays on the surface.
So yeah, the only way I've been able to visualize it is by just, if you're looking from above down onto the sphere, it looks like a straight line, but if you look from the side, it isn't. It's an arc of a circle.
Well, yes, but it
might not be a circle.
It is a circle. It is a great circle. It's like a line of longitude. Okay. But if we are if we're thinking of curvature as Euclidean eyes see it, we're talking about curvature every time, curved arcs, okay? Or we're talking about zero curvature as in the Euclidean plane. Now, if you look about the hyperbolic geometry on that surface, as you see on the right there, imagine it as your dip between two hills, but it curves down from front to back and up when you start in the middle of the dip and you go to left or right. Now, staying on that surface, your straight line on the surface, which, as Caroline says, if you look from above, it looks straight in the Euclidean sense, is seen from the side, it's a curve. But that's what we call negative curvature.
I've just realized something, Tony. This can actually be represented. I can actually make pictures when we do our eventually it's a really professional video of this. I can do this, all these three represented with bubbles, because you can easily make a sphere with bubbles. You can make a flat surface by putting it inside a flat surface. And I can make the hyperbolic shape with bubbles.
That would be very nice.
Wouldn't it?
And I have got a ball in South Africa that you can draw on, and you can represent these things. You can represent spherical geometry on it nicely, but you can do it with a ping pong ball and a fine pen, you know.
Or a balloon. Make a balloon nice and spherical.
Well, okay. You can. we'll try it sometime.
Hmm.
So now we'll come on to our circles. So imagine standing at the North Pole, and you go half a unit, half a meter or something, in every direction, and mark the points around you. There's all half a meter away from the North Pole. Okay. And that will be a circle on the surface of the Earth. You can do it on a balloon or on a ping pong ball. Okay.
Okay. Yep. So the center of that circle is the North Pole, and our circle is half a meter in radius away from the North Pole. Okay, that's the red circle that has the pi figure in the number 1. Okay, I'm there. I'm with you. I'm on the North Pole with you.
Now, if you draw a circle with diameter 1 on the flat plane, then the distance all the way around, which we call the circumference, is pi, and that's how pi is defined. It's the ratio of the circumference to the diameter of a circle, right? So the length of that circle, the length of that curve around the edge, the distance around the edge of the flat circle is pi. On the sphere, it's less than pi.
Yeah, and you can see why, because to make the shape, you have to be inside. To make it a Euclidean straight line, it has to go inside the sphere. So the line outside the sphere is going to be longer.
No, shorter.
It's less than pi. Sorry, shorter.
The line across. No, you're confusing, Caroline.
I'm getting it wrong.
You're confusing the line through, which is the straight line, with the line around, which is the circle.
Yeah, no, it's going to be more. It's like the triangle. Yes.
What is going to be more, Caroline? It is the Euclidean circle that's more than the one on the sphere. The circle on the sphere is shorter. The distance around the circle on the sphere is shorter.
Yeah, that's. You know what? I don't know if I said longer or short, but I meant shorter. I don't know what I said, but I meant shorter.
Okay.
And I know why I said it. I know what my mental representation is of it, but I might have it wrong.
So let's move to the hyperbolic geometry. Okay. Now then, imagine at the bottom of the dip there, between the two hills, right? Imagine drawing your circle, which are joining all the points that are exactly half a meter or half a unit from your center. Okay. And what will you get? You'll get a sort of bent sort of circle.
Yeah, you can have a circle.
And it will go on the saddle. It'll go down on the sort of flanks of the horse, as it were, and up towards the neck and tail of the horse. And in so doing, the flat circle will have to stretch if it's to go onto the surface of your saddle. So
if you had a model of that shape, which is that you could have there are things you can find that shape, or make one out of clay or something, and then you could put plasticine on to mold it into the actual shape that it would be, but you'd have to make sure it had a circle.
It's actually quite. You just imagine it. Close your eyes and think about it, and I think you'll be able to imagine it. Everybody out there. Okay, so the middle pictures there are parallel lines. Now, what you have, one of the Euclid's axioms was that if you have a line and you have another point that's not on the line, then there's one and only one parallel line to your given line, right? So you have at most two. You're specifying the distance apart. Well, you're specifying a point that's not on your first line, and then there's only one line through that point. Whereas
so there are many lines, because they can go.
No, there aren't many lines, Caroline. Not in the plane. There's only for any given line and a point not on the line. Let's call that P for this point that's not on the line. There's only one line through P parallel to your original line. And now for
right, so in other words, you've got a point that isn't on, it's away. It's somewhere that's not on that parallel line. There's only one place it goes, bing. There's only one place where it's going to be parallel to the parallel lines, perpendicular to the parallel lines.
No, not perpendicular, parallel. If you have a line, think of a line. I
don't think I've ever understood this when you said it. So I won't be the only one. So yes, please go ahead.
Please think of a line.
I'm thinking of a line. I've got a line.
Close your eyes and think of a line.
Got my eyes closed. I'm thinking of a line.
On a flat piece of paper.
It's on a flat piece of paper.
Now think of a point that's not on that line.
Okay.
Now you can only draw one parallel line through your away from it point that is parallel to your original line.
Right.
Only one.
Yes. Yes, I see it now. So I didn't start with two, because I'm looking at this image that has two lines that are parallel to each other. So I'm actually only starting with one. I'm starting with one line, and I've got to draw a parallel line that runs through point P. There is only one. Yes, on a flat Euclidean 2D surface, there's only one. Right, got you.
Now, if you then go to the sphere,
okay,
and you have a single line,
I'm drawing a single line on my sphere,
and then you take some other point of the sphere not on, so the lines are not going to coincide. They're not going to be the same line. That would be boring. They're going to be different lines. Your pair of lines are going to be different lines. Okay.
Well, I've got a point P that isn't on the original line, and I couldn't help myself. I had to complete the circle. My mind just completed the circle on the sphere.
Right. So then, what you got, to go back to the beginning, if you visualize this, you have got a line on the sphere, which is a great circle, and you take another somewhere else on the sphere, and every other line on the sphere, every others will intersect your great circle in 2 points. There are no parallels on the surface of a sphere.
See,
parallelism doesn't exist. Parallelism doesn't exist on the surface of a sphere.
See, in my imagination, I'm imagining a smaller circle. That's
not a straight. That is not a circle, Caroline. You've not got. Sorry, it might be a circle in your head, but it's not a straight line. We are talking about great circles, which are straight lines. Okay.
Right. I'm going to just leave it at that, and I can imagine. So I shouldn't be completing the circle then.
You could complete the circle as long as you're always talking about straight lines, and straight lines are great circles which cut the sphere, if you go through them, into two hemispheres. Now you can do that anywhere, right? You can cut your sphere into two hemispheres. Oh,
into two hemispheres. So it's halving. It's going to halve the circle. Yeah, the sphere. It's going to halve the sphere. Whatever it is, those 2 points. The great circle to complete it is going to halve the sphere. So if you halve the sphere, it's not possible for any other great circle that halves the sphere to
in another way, not to cut. It would necessarily cut.
Right, I've got it now. Okay, thank you.
There's no parallels on the surface of a sphere.
Okay, I see. So the great circle halves cuts the sphere basically into two hemispheres.
Right.
So so it's not possible. I've got it now. I've got it. I might have forgotten it tomorrow, Toni, but right now I've got it.
Right. So when you go to hyperbolic geometry,
right,
there are infinitely many parallels. So when you have a straight line in your hyperbolic geometry, there's always infinitely many lines that are equidistant from it somewhere else in the geometry.
Okay.
Like, you've got to think of parallels as railway lines on the flat surface, all right? And in hyperbolic geometry, there's there's infinitely many parallel lines parallel to a given line. Okay, so let's move on to triangles. Okay, it's pretty well known that if you have any triangle, any shaped triangle, not just an isosceles one as here, the three angles of the triangle add up to 180 degrees.
Yep.
Now, in spherical geometry, they add up to more than 180 degrees because of the positive curvature.
Yep.
And in hyperbolic geometry, because of this effect of negative curvature, the angles add up to less than 180.
Mm-hmm.
Isn't that amazing? I think it's lovely.
I agree. It's mind-boggling and it's lovely, and I still think it's amazing that Escher was able to create these representations of this mathematics without being a mathematician.
Now here's a couple of Escher woodcuts, dating from a little later on in his life, 59 and 64. They're both of the same subject. Okay, they're both fishes, and again it has got this symmetry here, where you've got three fishes' noses meeting at a point with the tails between them. Okay, here you have, on the left, you have a very strange thing that's not really it's strange, because it's really, in speaking, it's supposed to be on the plane, and the fishes get smaller as they get to the edge. Now, Escher was doing that sort of exploration of infinity and getting gradually smaller and smaller forever and ever towards the edge. He was doing that sort of exploration quite early on in his career, much before this particular one I've picked out to show. And he then, as I understand it, he then met with a mathematician called Harold Coxeter, when Coxeter came to a conference in Europe. And Coxeter was intrigued by Escher's work because Coxeter was a geometer, one of the leading geometers of his time. And he was working in hyperbolic geometry, where they use this spherical, not spherical, I don't mean that, they use this circular unit circle as a model of the hyperbolic plane. And because you define distance differently in hyperbolic geometry, right, it has a different definition. By the definition of distance in hyperbolic geometry, all those fishes are hyperbolically the same size.
And that's what we saw with the circle in that 2 slides before, which again is...
So that is Escher playing with this concept of the limit in a square limit and a circle limit. In fact, he did a whole series of both of them. This is circle limit 3. That is our exploration for today of Escher, but there is so much more. And so we're going to do another Happy Maths Hour on Escher, aren't we, Caroline?
Yes, thank you for joining us. And Toni and myself, Happy Maths Hour. See you next week. Thank you. For greater understanding and enjoyment of mathematics, the Maths Toys YouTube channel is brought to you by AIMSEC and the Aiming High website. In the description, you will find a link to our home learning guide for ages 4 to 18 and a teacher resource pack. If you find this video useful, there is a GoFundMe link in the description to donate to and support AIMSEC. The money goes to bursaries for professional development for teachers in disadvantaged communities around the world. Subscribe, comment and ding the notification bell to make sure you don't miss our latest activities.